Software development is the fascinating process of creating computer programs. Think about the apps on your phone, the websites you visit, or the games you play. All of these are examples of software. Skilled individuals, known as software developers, use their knowledge of programming languages and design principles to build these digital tools. It's actually a creative endeavor, much like an architect designs a building, but instead of bricks and mortar, developers use lines of code. This code tells the computer exactly what to do step by step to achieve a specific outcome. The world around us is increasingly powered by software, making this field incredibly important. The importance of software development cannot be overstated in our modern society. From the systems that manage our banking and healthcare to the entertainment platforms that connect us, software is the invisible engine driving much of our daily lives. Imagine a day without your smartphone, your email, or even the traffic light systems that manage our roads. Many of these conveniences rely heavily on intricate software. Businesses use software to manage their operations, scientists use it for complex research, and artists use it to create digital masterpieces. The ability to develop robust and reliable software is therefore a critical skill in the 21st century, impacting nearly every industry imaginable. Understanding software development is not just for aspiring programmers, it provides valuable insight into how the digital world functions. When you grasp the basics of how software is made, you gain a new appreciation for the technology you use every day. It helps you understand why some apps are user-friendly and others are frustrating, or why updates are regularly released for your favorite programs. This knowledge can empower you to be a more informed user of technology, and even to identify potential areas where new software could solve existing problems. It's about looking behind the curtain of the digital stage to see the intricate work involved. Ultimately, software development is a blend of logic, problem-solving, and creativity. It involves understanding a need, designing a solution, and then meticulously building that solution piece by piece. It's a field that is constantly evolving, with new technologies and methodologies emerging all the time. This dynamic nature makes it an exciting and challenging domain to explore. Whether you aim to build the next big social media platform or a small utility to help with your daily tasks, the journey of software development starts with understanding these fundamental concepts and the immense potential held within lines of code. Embarking on a software project without a clear process is like trying to build a complex machine without any instructions or blueprints. You might end up with something, but it's unlikely to be what you intended, and it will probably be riddled with problems. A software development process, often called a software development lifecycle or SDLC, provides a structured framework for creating high-quality software. It breaks down the enormous task of building software into manageable stages, each with its own objectives and deliverables. This systematic approach helps teams stay organized, manage resources effectively, and reduce the chances of costly errors later on. Following a defined process brings numerous benefits to a software project. Firstly, it improves communication among team members and stakeholders. When everyone understands the current phase of development and what is expected, collaboration becomes smoother and more efficient. Secondly, a good process helps in identifying potential risks and issues early on. For instance, thorough planning can reveal technical challenges before any code is even written. This proactive approach saves time and money by preventing major problems from derailing the project. It also allows for better estimation of timelines and budgets, leading to more predictable outcomes and happier clients or users. Different projects may call for different types of development processes. Some well-known methodologies include waterfall, where each phase must be completed before the next begins, and agile, which emphasizes flexibility, collaboration, and iterative development in short cycles. For example, building a critical safety system for an airplane might use a very rigorous sequential process to ensure every detail is perfect. In contrast, developing a new mobile app where user feedback is crucial might benefit from an agile approach, allowing for rapid changes based on that feedback. The key is to choose a process that best fits the project's specific needs and constraints. Without a structured process, software projects can easily fall into chaos. Scope creep, where new features are endlessly added without proper planning, can lead to delays and budget overruns. Poorly defined requirements can result in software that doesn't meet the user's needs. A lack of testing can release buggy products that frustrate users and damage a company's reputation. Therefore, a well-thought-out software development process is not just a suggestion. It's a fundamental requirement for successfully delivering software that is reliable, maintainable, and truly valuable to its intended audience. It's the roadmap that guides the journey from an initial idea to a fully functional product. The very first step in any successful software development journey is planning. This is where the initial idea for the software begins to take shape. It starts with identifying a problem to solve or an opportunity to explore. For instance, you might notice that local community groups struggle to organize events, leading to the idea of an app to simplify event management. During this phase, developers and stakeholders discuss the core purpose of the software. What will it do? Who will use it? What specific goals should it achieve? Answering these fundamental questions clearly is essential before any further work begins, as they form the bedrock of the entire project. Once the basic idea is established, the next crucial activity is gathering requirements. This involves detailing exactly what the software must do. These requirements can be functional, describing specific features like users must be able to create an account, or the system must generate a monthly report. They can also be non-functional, specifying qualities like performance, such as the website must load in under 3 seconds, or security, like user data must be encrypted. Collecting comprehensive and unambiguous requirements is vital. Imagine building a house without knowing how many rooms are needed or what style the owner prefers. The result would likely be unsatisfactory, and the same applies to software. Effective requirements gathering often involves talking to potential users, conducting surveys, analyzing existing systems, and holding workshops. If you were building that community event app, you would talk to event organizers and attendees to understand their pain points and desired features. It's important to document these requirements carefully, often in a document called a Software Requirement Specification, or SRS. This document serves as a contract between the development team and the client or stakeholders, ensuring everyone has a shared understanding of what is being built. Misunderstanding requirements is one of the most common reasons software projects fail or go over budget. The planning and requirements phase concludes with an assessment of feasibility. Can this software actually be built with the available resources, technology, and time? What are the potential risks involved, and how can they be mitigated? This might involve creating a rough project plan, estimating costs, and outlining a preliminary schedule. For example, if the community event app requires complex real-time GPS tracking, but the team has no experience with it, that's a risk to address. Skipping this careful planning stage is like setting sail without a map or a compass. You might eventually reach land, but it's unlikely to be your desired destination. After the planning phase has clearly defined what the software needs to do, the design stage focuses on how it will do it. This is where developers and architects create a blueprint for the software system. It's about making high-level decisions regarding the overall structure, components, and their interactions. Think of it as an architect designing the structural framework of a building, deciding on the materials, and how different rooms and utilities will connect. For software, this involves choosing the right technologies, defining the database structure if one is needed, and outlining how different modules of the software will communicate with each other efficiently and securely. The design phase typically has two main aspects: high-level design and low-level design. High-level design, also known as architectural design, provides an overview of the entire system. It identifies the major components and their relationships. For instance, if we're designing an e-commerce website, the high-level design might show separate components for user accounts, product catalogs, the shopping cart, and the payment processing system. It would define how these components interact, perhaps through application programming interfaces or APIs. This big-picture view ensures that all parts of the system will work together cohesively. Low-level design, on the other hand, delves into the details of each individual component or module. It specifies the data structures that will be used, the algorithms that will be implemented, and the specific functions or classes within each module. For our e-commerce example, the low-level design for the shopping cart module would detail how items are added or removed, how quantities are updated, and how the total price is calculated. This detailed design acts as a guide for the programmers during the coding phase, helping them write code that is consistent with the overall architecture and meets the specific requirements of each part of the system. A well-thought-out design is crucial for creating software that is not only functional but also maintainable, scalable, and robust. Good design anticipates future changes and makes it easier to add new features or fix bugs later on. It considers aspects like performance, ensuring the software runs efficiently, and security, protecting user data and system integrity. For example, designing a system with modular components means that if one part needs to be updated or replaced, it can be done without affecting the entire application. Rushing or neglecting the design phase often leads to complex, difficult-to-manage code and costly rework down the line. With a solid plan and a detailed design in hand, the next phase is coding, also known as implementation or construction. This is where software developers translate the design documents into actual working computer programs by writing lines of code in a chosen programming language. It's the phase where the abstract ideas and blueprints become tangible software. Developers use their expertise in languages like Python, Java, JavaScript, or C++ to instruct the computer on how to perform the tasks specified in the requirements and design documents. This requires careful attention to detail, logical thinking, and a deep understanding of programming principles. During the coding phase, developers often work on individual modules or components of the software. For a large project like a social media platform, different teams might work on different features simultaneously. One team on the user profile system, another on the newsfeed, and yet another on the messaging functionality. It is essential that developers follow coding standards and best practices. This includes writing clear, readable, and well-documented code. Code that is easy to understand is also easier to debug, maintain, and enhance in the future, not just by the original author but by other team members as well. Good coding practices also involve writing code that is efficient and secure. This means optimizing algorithms to ensure the software runs quickly and doesn't consume excessive resources like memory or processing power. It also means being mindful of potential security vulnerabilities, such as SQL injection or cross-site scripting, and writing code that defends against such attacks. For example, when developing a login system, developers must ensure that passwords are stored securely and that the system is protected against unauthorized access attempts. This meticulous approach to construction is what separates robust professional software from amateur attempts. The construction phase isn't just about blindly typing out code. It often involves problem solving and iterative refinement. Developers might encounter unexpected challenges or realize that a particular part of the design needs adjustment. They use tools like integrated development environments or IDEs, which provide features like code editors, debuggers, and build automation tools to make the coding process more efficient. Version control systems such as Git are also crucial for managing changes to the code base, allowing multiple developers to collaborate effectively and revert to previous versions if necessary. This phase is truly where the software comes to life, line by meticulous line. Once the code has been written, the software enters the crucial testing phase. The primary goal of testing is to find and fix errors, often called bugs or defects, before the software is released to users. No matter how skilled developers are, mistakes are inevitable in complex software. Testing is the systematic process of executing the program with the intent of finding these errors. It involves verifying that the software meets all specified requirements and functions correctly under various conditions. Thorough testing is absolutely essential for delivering a high-quality product that users can trust and rely on. There are many different types of testing, each serving a specific purpose. Unit testing focuses on individual components or modules of the software to ensure they work correctly in isolation. For example, a unit test for a calculate total price function would check if it correctly sums item prices and applies discounts. Integration testing then checks if these individual modules work together as expected when combined. System testing evaluates the complete integrated software system against the original requirements. Finally, user acceptance testing, or UAT, is often performed by the actual users or clients to ensure the software meets their needs and is fit for purpose in a real-world scenario. During testing, testers design test cases. A test case is a set of conditions or variables under which a tester will determine whether a system is working correctly. For example, a test case for a login feature might include testing with a valid username and password, an invalid username, an invalid password, a blank username, and so on. Testers meticulously execute these test cases and document any discrepancies between expected and actual outcomes. These discrepancies, or bugs, are then reported back to the developers for fixing. This iterative cycle of testing, bug fixing, and retesting continues until the software reaches a satisfactory level of quality. Skipping or rushing the testing phase is a recipe for disaster. Releasing buggy software can lead to frustrated users, loss of revenue, damage to a company's reputation, and in some critical systems, even severe real-world consequences. Imagine a banking application that miscalculates balances, or a medical software that displays incorrect patient information. The cost of fixing bugs after release is significantly higher than fixing them during development. Therefore, investing time and resources in comprehensive testing is not an expense, but a critical investment in the quality and success of the software product. It's about ensuring the software is not just built, but built right. After rigorous testing has confirmed that the software is stable, reliable, and meets all requirements, it's time for deployment. Deployment is the process of making the software available for users. This can take many forms depending on the type of software. For a web application, it means installing it on web servers, so users can access it through their browsers. For a mobile app, it involves submitting it to app stores like Google Play or Apple's App Store. For desktop software, it might involve creating an installer package that users can download and run on their computers. Careful planning is needed for a smooth deployment to minimize any disruption to users. The launch of the software is an exciting milestone, but it's not the end of the software development journey. Once the software is live and being used, it enters the maintenance phase. Maintenance involves monitoring the software's performance, fixing any new bugs that are discovered by users in the real world, and making updates or enhancements over time. Users might report issues that weren't caught during testing, or new security vulnerabilities might emerge that need to be patched. For example, an online retail platform might need regular updates to add new payment methods or to improve its product search functionality based on user feedback and changing market trends. Maintenance can be categorized into several types. Corrective maintenance involves fixing bugs and errors found after release. Adaptive maintenance involves modifying the software to keep it compatible with changing environments, such as a new operating system version or updated hardware. Perfective maintenance involves improving the software's performance or adding new features based on user requests or business needs. Finally, preventative maintenance involves making changes to prevent future problems, such as refactoring old code to improve its readability and maintainability. This ongoing care is crucial for the long-term success and longevity of any software application. The maintenance phase can often consume a significant portion of the total software lifecycle cost. Well-designed and well-documented software is generally easier and less costly to maintain. This is why the principles of writing clean code and thorough testing discussed in earlier phases are so important. They directly impact the effort required during maintenance. Regularly updating and maintaining software ensures it remains useful, secure, and efficient for its users over its entire lifespan. It's about ensuring the software continues to deliver value long after its initial launch, adapting to new challenges and opportunities as they arise. To build software, developers rely on a variety of programming languages and tools. A programming language is a formal language comprising a set of instructions that produce various kinds of output. Different languages are suited for different tasks. For example, Python is widely popular for its readability and versatility, often used in web development, data science, and artificial intelligence. JavaScript is the cornerstone of front-end web development, enabling interactive elements on websites, but with Node.js, it's also powerful for back-end development. Java is a robust, object-oriented language commonly used for large-scale enterprise applications and Android app development. Choosing the right programming language often depends on the project's requirements, the target platform, and the team's expertise. For mobile app development, Swift is the primary language for iOS apps, while Kotlin and Java are popular for Android. For game development, C++ is often favored for its performance, along with game engines like Unity, which uses C#, or Unreal Engine, which uses C++. C# is also a versatile language developed by Microsoft, widely used for Windows applications, web services with .NET, and game development with Unity. Beginners often start with languages like Python or JavaScript due to their relatively gentle learning curves and large supportive communities. Beyond programming languages, developers use a suite of tools to streamline their workflow. Integrated development environments, or IDEs, are essential. IDEs like Visual Studio Code, IntelliJ IDEA, PyCharm, or Eclipse provide a comprehensive set of tools in one place. a source code editor with syntax highlighting, build automation tools, and a debugger for finding and fixing errors. These features significantly enhance productivity and make the coding process more manageable. For instance, a debugger allows a developer to step through code line by line, inspect variables, and understand how the program is behaving, which is invaluable for troubleshooting complex issues. Other critical tools include version control systems, with Git being the most widely used. Git allows developers to track changes to their codebase, revert to previous versions if something goes wrong, and collaborate effectively with other team members on the same project. Platforms like GitHub, GitLab, and Bitbucket provide hosting for Git repositories and offer additional features for collaboration, code review, and project management. Furthermore, various testing frameworks, build tools like Maven or Gradle, and continuous integration and continuous deployment pipelines are all part of the modern developer's toolkit, helping to automate processes and ensure software quality from development through to deployment. Starting your journey into the world of software development can be incredibly exciting and rewarding. For beginners, the sheer volume of information and technologies might seem daunting at first, but remember that every expert developer was once a beginner. The key is to start small and be consistent. Choose one programming language that interests you and is beginner-friendly, such as Python or JavaScript. Focus on understanding the fundamental concepts like variables, data types, control structures like loops and conditional statements, and functions. Don't try to learn everything at once. Master the basics first, as they form the foundation for more advanced topics. One of the best ways to learn programming is by doing. Theoretical knowledge is important, but practical application solidifies your understanding. Start working on small projects as soon as possible. This could be a simple calculator, a to-do list app, or a basic text-based game. These projects will not only help you practice your coding skills, but also give you a sense of accomplishment and keep you motivated. Don't be afraid to make mistakes. Errors are an integral part of the learning process. Learning how to debug your code and troubleshoot problems is a critical skill for any developer. The software development community is vast and incredibly supportive. Take advantage of the numerous online resources available, such as tutorials, coding websites like Free Code Camp or Codecademy, forums like Stack Overflow, and open source projects on GitHub. Joining online communities or local coding meetups can provide you with opportunities to learn from others, ask questions, and collaborate on projects. Reading code written by experienced developers can also be a great way to learn best practices and discover new techniques. Remember, you are not alone on this journey, and there are always people willing to help. Finally, be patient and persistent. Learning to code takes time and effort. There will be moments of frustration when you get stuck on a difficult problem, but overcoming these challenges is what makes the learning process so fulfilling. Celebrate your small victories along the way. Keep practicing, keep learning, and stay curious. The world of software development offers endless opportunities for creativity, problem-solving, and innovation. Your coding adventure is just beginning, and with dedication and passion, you can build amazing things and contribute to shaping the future of technology. Start today, write your first line of code, and unlock your potential.